Maths Aspirants is a collective of students, research scholars, and teachers who loves mathematics, initiated by myself in 2017. We used to arrange online problem solving sessions and online test series to help the students who prepare for different competitive examinations since the lockdown time. As a part of that online problem solving session series, today we have a special guest. We have Ms.Rosna from Austria. I am very happy to introduce Rosna to you. Ms. Rosna, now pursuing PhD at Graz University of Technology, Austria. She has done BSc Mathematics from Sacred Heart College, Thevara, and she secured first rank in MG University for BSc. And after that, Rosna joined for MSc at Cochin University of Science and Technology, and again she secured first rank for MSc and then did MPhil from Cochin University of Science and Technology. During that MSc time itself, she qualified CSIR Dec with JRF. Also, she is a recipient of Inspire Fellowship, She Scholarship, KSCSTE, an initiative of Government of Kerala, Research Fellowship. So, the story of Rosna is actually very inspiring and motivating for any prospective student. So I'm sure that everyone will get really benefited out of today's session. Today, she will discuss with us some topics related with uniform convergence of sequence of functions. In 2020, she has done one session on linear algebra in our platform, and that is available in our YouTube channel. So I'm very happy to welcome Rosna to this program, and I use this opportunity to express my sincere gratitude and love to Rosna being with us. I welcome everyone to this program. Welcome, Rosna.
Thank you so much, sir, for these beautiful words. So today I'm going to talk about uniform convergence. So I hope that throughout the section you are already familiar with the convergence of real numbers. So I will not discuss about that again. So I will just go through the uniform convergence. So here the convergence of functions. Okay, what is a point-wise convergence? So here you have a sequence of functions which is from x to r. And I want to say that this function converges to some other function. So we have to define some notion of saying that when this collection of or the sequence of functions converges to something. So the first notion is the point-wise convergence. The definition is for all x belongs to x and for all epsilon greater than 0, there exists an n belongs to the natural number such that for all n greater than or equal to n, the distance from fn of x to f of x, so or the difference between fn of x and f of x is less than epsilon. This is the formal definition of point-wise convergence. To understand it more easily, you can consider that if you fix any x belongs to x, our function fn of x should converge to the function f of x. So in the point, so if you're putting evaluating your function at the point x, then that sequence should converge to f of x. So this is the easy definition or the equivalent definition of point-wise convergence. So how to check given sequence of function is point-wise convergent or not? So this is the same as I explained before. You take some x belongs to x. You put this x to the function fn. So you evaluate fn at the point x0. And if you evaluate f1 of x0, f2 of x0, and so on, you will get a sequence that is y1, y2, y3, and so on. So when you plug the x0 to your function fn, you will get a sequence of real numbers. Now we check whether the sequence of real numbers converges to f of 0. If it's so, yes, at this point it is converging, but we want to know whether the whole function is convergent, so we have to repeat it for every x belongs to x. So this is the theoretical definition of how to check whether the sequence of function is pointwise convergent or not. I will explain this with a picture so that it will be easy to remember. For example, the set of given functions I have is of the form x by n, where x belongs to 0 to infinity. And then your functions will be looking something like this. Our f1 is x because x by 1 is x. So this is your f1, this is your f2, f3, f4, and so on. So it is going like this. And we would like to know whether this function is convergent to 0 or not. For that, first I will pick some x0. So here my x, I took it as 4000. So at the point 4000, I draw a vertical line. And when the vertical line touches my f1, so that point is my y1, that is f1 of 4000, which is 4000. So the first point is 4000, the second point is 2000, and so on. So here I'm getting a sequence which is y1, y2, and so on. So if you put f10, you will get 400, and so on. So this gives you a sequence, y1, y2, y10, and so on. And we check where the sequence converges to. And from the picture, it is very clear to observe that this sequence converges to the function 0. So it is going to 0. So if you put x equal to 4000, your sequence is converging to 0. But this only shows that the point x equal to 4000 is going to 0. But we want to know where this function, the entire function, is going. So we take different values of x and compute different sequences and see where they are going. In all these cases, we know that it is going to 0. So we can say that the sequence of functions is going to a sorry. Is that clear?
Yes, ma'am.
Okay, thank you. So here, if you check for each value of x, and if it is convergent to our function, then we can say that the sequence of functions is converging to the limit function. Now, in this case, this is called the pointwise convergence. You can also remember from the name, it is pointwise. For each point, it is convergent. So you can remember it as a pointwise convergent. Then let's check to come back to the epsilon definition. So what does this epsilon definition says about us? So here the definition, as the definition, if you look at it, you have to show that for all x belongs to x and for all epsilon greater than 0, there exists an n belongs to n such that this condition is satisfying. So here our main target is to find an n. If you could find such an n, then it is pointwise convergent. So how to find this n? For that, I consider the inequality. So we have to satisfy this inequality. So we take fn of x minus f of x. Since f of x is 0 always, we can replace it by x by n. And we want it to be less than epsilon. So since all our values are positive, so we can remove this modular function. So you are only getting x by n, which is less than epsilon. Here you can do a symbol exchange and you can see that x by epsilon less than n. So whenever x by epsilon is less than n, then this condition holds. So we need to find an n such that this condition holds, which means that if you take any n which is larger than this n, then we are done. So if you put n equal to x by epsilon, then our condition is satisfied, so our function is pointwise convergent. And to understand a bit more about what is happening here, I just redraw in this form. So this is not the exact form of how the function looks, because as you can see, the function are getting very close to each other. So it will be difficult to see where these functions are. So I just redraw it in this form to just analyze what is happening here. So as I said, I am given some x and epsilon, and with respect to that, I am choosing my n. For example, if I put x equal to 250 and I am just making epsilon equal to 1 for this case, and then what should be the n we want to take? So since we have a formula, it is easy to calculate. It is should be 250. So what does this mean? So if you have x equal to 250, so this is the x value, you have 250. And if you consider the distance of fn of x from the f of x, and the distance is, we said that it should be less than 1. So you are looking at the a block or distance from 0 to 1, and you are looking at which all fn's fall inside this block. And this is what we have just showed. If n is 250, then all the functions above 250, so 250, 500, and whatever above it is, will fall into this distance. So that is our n. But if I change x equal to 500 and I keep epsilon as 1 itself, then what should be my n? So in this case, n will be 500. So before it was 250, so all the functions more than have the value more than 250 will fall into this portion. But when I put x equal to 500, some of the functions which were already in this block was gone out, so they are not valid now. So now we can only say that all the functions which are 500 or more will lie into the block. So I'm just repeating the process. So I took next value x equal to 1000 and so on. So for 1000, I'm getting 1000, then the next value and so on. So here you can see that for each value of x, the n is changing. For here, it is 250, here it is 500, 1000, and so on. But remember, I always kept epsilon 1. So I'm just fixing epsilon equal to 1. I'm just changing x. And you can see that the value of n is changing. But this is fine for us because we just need to find n and to satisfy this condition. If we can find this n, then we are done. So here there is no issue. So we can say that the function is pointwise convergent. But this leads to a different definition, that is the uniform convergence. So pointwise convergence is a one way of defining how the functions are converging to a different function. But here, one important point to note is that the n we are choosing is depending on both x and epsilon. So if the n is depending on x and epsilon, then we can only say that it is pointwise convergent. But if you want to say something is uniformly convergent, as the name suggests, there is something happening uniformly to everyone. So this uniformly comes with the n, because for uniformly convergence, n only depends on epsilon. So now let's look at the definition of uniform convergence. So it is, if you look at the definition, it is very similar. You just change pointwise to uniform and you just take the for all x belongs to x from here to here. So when you look at the first glance, you might not see what's the difference is, but the difference is the n. So what the n depends on. So in this case, n only depends on epsilon, and the n should work for all x belongs to x. So, so that is the condition. Let's come back to our example. So in this case, we know that for each value of x, we have a different n. But for our uniform convergence, if we want to make it to say that this is a uniform convergent, we have to find an n which is satisfying for all values of x. So here again, I am fixing my epsilon equal to 1. So the distance between fn of x and f of x is 1. But I want to see which functions lies entirely in this epsilon strip. So here in this picture, you can easily see that, okay, this is the from 4000 onwards, it's lying inside. And here, just note that I'm not drawn it for 0 to infinity. That's why I'm just saying that it's on up from 4000 on. For representation, I'm just assuming my range is from 0 to 4000. So if you assume that your range is from 0 to 4000, then you can clearly say that from n equal to 4000 onwards, the functions lie completely inside this epsilon bound. So if you can find such an n for your all values of x, then you can say that the function is uniformly convergent. But if you couldn't find such an n, then you cannot say it. So this is the case where epsilon is fixed. So I am just dealing with a fixed epsilon. But if you want to show that a function is uniformly convergent, I have to check it for all values of epsilon. So let's look at that. For the first case, my epsilon is fixed as epsilon 1. So assume that this is my epsilon 1 bar or the strip. And I want to find an n such that the function entirely lies inside it. So how we can find it? So the one of the easiest, I cannot say that the easiest, but one of the method to show is that you calculate the distance of the function, the fn of x minus f of x, and you take the supremum. And if the supremum of this function in your range from 0 to 4000 is inside epsilon, then the entire function will be inside epsilon. There is also I have done a slight change here because I only consider the positive part because my function only have positive values, but otherwise it's from epsilon 1 to minus epsilon 1. So here I'm only taking the small portion, so you can also consider this is extending to the bottom also. So in our example it doesn't make sense, so that's why I avoided it, but it's actually an epsilon strip around your function f of x. So it should be in this way and this way. That's why we're taking the modulus. So here in this case, if you want to find on which n is inside this epsilon bound, you take the supremum value of fn of x minus f of x in the range and see, okay, whether this value lies inside or not. So for the first case, this n is 250, then we are okay, done. And then I take the next epsilon, which is slightly less than the previous one, and I have to satisfy it for all epsilon. So here also I should be able to find some n. And for that, I again use the same formula, and I reduce the width of the strip and so on, so on. And finally, my width of the strip is tending to 0. In that case, the supremum of fn of x minus f of x should be tending to 0. If you can satisfy this condition, then your function is uniformly convergent. So this is nothing but what we call the MN test. That is, if you have a sequence of functions such that it is point-wise convergent, that is limit n terms to infinity fn of x equal to f of x for x belongs to the range, so in the domain, then you are taking Mn. Mn is nothing but the supremum of the difference between fn of x minus f of x. Then the function is uniformly convergent on AB if and only if Mn converges to 0 as n terms to infinity. So this is the Mn test which we use for to show that the function is uniformly convergent or not. And this is a very nice result, and this is very useful while solving the problems for competitive examinations. And we mainly use this test. And there are also some properties which you can relate to the uniform convergence. The first nice property is that uniform convergence preserves continuity, which means that if you have a sequence of functions, these functions are continuous, and if these functions converges uniformly to an f of x. So our given functions, the sequence of functions in which everybody are continuous, and this sequence of function converges to a function, then we get an additional knowledge of this function is that the limit function is also continuous. And how we can use this property for finding whether the given sequence is convergent or not. So how we use is that, so if you are given with a sequence of functions which are continuous, and we know that their limit function is discontinuous, then their convergence cannot be uniform. Because if the convergence is uniform, the limit function should be continuous. So if you already get the limit function as discontinuous, you can immediately tell that, okay, the convergence is not uniform. So this is also a nice method in which you can use to show that a given sequence of function is uniform, convergent or not. So the other properties of the uniform convergence is the relation between the uniform convergence and integrations. So here what we say is that if you have a sequence of functions which is continuous and it converges uniformly to another function f, then the limit and the integration can be interchanged. So limit n terms to infinity, integral of your functions is same as integral of limit of your function, so which is integral f of x dx. So integral and limit can be interchanged if the convergence is uniform. I hope that you understood the definitions so far. Okay, let's go to the first question. So I have introduced what is a uniform convergence and x by n. So what do you think about this function? Is it uniformly convergent or not? Can you answer in the chat box? Let me try to see whether I can see your chat box. Do you have any idea of whether this function converges or not? I'm not seeing any messages. Did somebody else could see it? Okay. So I will share once again. You just check the domain also. What is the domain of the function? So my x is from 0 to infinity. So whether this function is uniformly convergent. The answer is no, actually, because you have seen that your n, you need an n to satisfy for all x, and this n is x by epsilon. But this x, you cannot bound it because x goes to infinity, so you cannot bound that x for you. So if you take the supremum, this x is going to infinity. So in this, the whole bound, it cannot be convergent. But if I restrict my function to 0 to 4000, then the function is convergent because I can put my x as 4000, then you will get a something divided by n, and n goes to 0. So we are done. Okay, let's move to first question. Let fn of x is equal to x raised to 1 by n for x belongs to 0, 1. Then I have four options. The first one is limit n times to infinity fn of x exist for all x belongs to 0, 1. The second option is that limit n times to infinity fn of x defines a continuous function on 0, 1. And third, fn converges uniformly on 0, 1. And fourth, limit n times to infinity fn of x equal to 0 for all x belongs to x. So could you try to solve this question? I will give you around 30 seconds. I think that will be enough. Could you also give me the answers in the chat box, and then we can discuss about the solutions. And in the meantime, let me try to connect my other device so that I can see your answers. Okay, I think there are some options. Option A, option C. Okay, then let me try to solve this question. So here, if you take f(n) of x equal to x raised to n, and if you put x equal to 0, you have your function to 0. And for all values between 0 and 1, you will get the function value as 1. So you're getting a discontinuous function, but the f(n) of x converges in each point, but it is converging to a discontinuous function. So what was the options? This first option was limit n times to infinity f(n) of x exists for all x belongs to 0, 1. Yes, that is true, it exists. But the second option says that it defines a continuous function. No, that is wrong because it is not a continuous function. And this third one, we are using the property of uniform convergence and the continuity. Here, their fn's are continuous, and if it is converges uniformly, then the limit function should also be continuous. But we just saw that the limit function is not continuous, so it cannot be converges uniformly. And the fourth option is clearly not true because it also takes the value 1 for some values of x. So the option A is correct. Is that clear?
Yes, ma'am.
Okay, thank you. Let's see the second question. So here, let fn is a function from 1, 2 to 0, 1. And the function is given by fn of x equal to 2 minus x raised to n for all non-negative integers n. And f of x is the limit function. Then which of the following is true? A, f is continuous on the range 1 to 2. And B, fn converges uniformly to f in this range. C, the limit can be interchangeable. D, for any a belongs to the open 1, 2, we have the limit and the differentiation cannot be interchanged. So these are the 4 options. I will maybe I will give you around 45 seconds. Let's see whether you can solve it. And I will look into the chat. Okay, so there are option D. Okay, let's see the solution. So first we have to show that whether f is continuous. So we have to find what should be the f. So we are taking fn of x, which is 2 minus x the whole raised to n. And this function is 0 for x between 1 and 2, and it is 1 for x equal to 1. So clearly, this function is not continuous. So this is a discontinuous function. So the first option is clearly wrong. And the second question is whether it converges uniformly to f. So this is also follows the same rule. We check whether the fn's are continuous. If they are continuous, then if they are uniformly converging to f, then f should be continuous. But here, fn's are continuous, but f is not continuous. Then you can clearly say that the B is not true. The third case is that whether this limit n terms to infinity integral is equal to the integral of the limit function. So for that, we have to check it. So the limit 1 to 2 fn of x dx is limit 1 to 2. I'm substituting the value here, 2 minus x raised to n dx. And you find the integration of it, and when you put the value of 1 and 2, you will get a function. And if you take the limit n terms to infinity of this integral, it goes to 0. And if you consider f of x, this is 0 for this range and 1 for x equal to 1. So their integral f of x is equal to 0. So you will get limit n terms to infinity of this value is 0, and integral 0 to n of x dx equal to 0. Hence, they are equal. So the C option is correct. Now we have to check what happens for the D. So for the D, what we have to say that we have to find the derivative of your sequence of functions fn, and you have to find the limit n terms to infinity, what happens to these derivatives, and then we have to check what is the derivative of your limit function. So now I consider fn of x, and its derivative is this one. And for limit n terms to infinity, fn dash of x is the limit of this function, which goes to 0. So the limit of fn dash of x goes to 0. But what happens to the derivative of f of x? But here we are taking derivative on the open interval 1 and 2. So the function itself is 0. So the derivative is also 0, but they are equal. So the limit n terms to infinity f dash of n f of x is equal to f dash of x. But in my question, it's given that it is not equal. Hence, the option D is wrong. So the only option is C. I hope this question is also clear to you.
Yes, ma'am.
Yeah, thank you. Now let's go to question 3. Here I have only 2 options. Which of the following is uniformly convergent? For the first function is fn of x equal to n square x into 1 minus x raised to n. When you are considering a function, you always look at the domain of the function, because the uniform convergent thing will change according to the domain. So it's from 0 to 1. And for the next question, the next option is fn of x equal to x e raised to minus nx square for x belongs to R. So are these both options correct, or only one option is correct? And which one is correct? I will give you again maybe 45 seconds to solve it. So what you have to do, you have to first see what is the pointwise convergent function is. And if the pointwise convergent function is discontinuous, just check whether your functions are continuous, then you can get an answer immediately. Otherwise, you have to use the MN test. Okay, I got some answers. Okay, let me check which answers are correct. Now first consider the first function, that is fn, which is n square x into 1 minus x raised to n. The first task is to find where it is converging to. It's clear that it is converging to 0, and why? Because you have to, so your domain is in 0, 1. You put x equal to 0, you will get 0. For x equal to 1 also 0. So you only have to look for those values between 0 and 1. And there you will get 1 minus x will be of something between 0 and 1. And you know that if your points are between 0 and 1, if you raise to power n, it will go to 0. So this function converges to 0, which is a continuous function. So there is a hope that maybe a function is uniformly convergent or not. But in this case, we cannot say something directly. So we have to check with the MN test. So this only thing we can say is that it's pointwise convergent. So what about the uniform convergence? For that, I take Mn, which is the supremum over closed interval 0, 1, where we had to find the fn of x minus f of x. Since f of x is 0, you can just plug in this function. But now in this interval, we have to find what is the supremum of this function. So one method to find the supremum is to take the derivative of the function and equate it to 0, and then you will get some points which has the maxima or minima. Then you have to see which points gives the maxima or minima. So here, when I equate it to 0, you will get the derivative of f of x is this one, and when I equate it to 0, you will get this thing. But here, if you want to cancel out these terms, you have to make sure that x is not equal to 1. So one point is that what happens x is equal to 1. When x equal to 1, you will get fn dash of x equal to 0. But for the other values, what the possibility is that x is equal to 1 by n plus 1. Here also f dash of n equal to 0. So the maximum you will get is when you substitute the values, the maximum you will get is 1 divided by n plus 1. So when x equal to 1 divided by n plus 1, this function gives the maximum value in the range. So just put x equal to 1 divided by n plus 1, then you will get something like this. So this is your supremum function. But we have to say that m1 goes to 0, then only we can say your corresponding sequence is uniform convergent or not. Now let's see whether this converges to 0 or not. But here, if you put limit n times to infinity, you can replace this at 1 n by e, but this goes to infinity. So this means that mn does not converges to 0. Hence, the function, the sequence of function does not converge uniformly. So by the MN test, we have showed that this does not converge uniformly, which means that option A is wrong. Now let's check what is the option B is. Again, we have to see to which function fn converges to. So our fn is x into e raised to minus nx square, and this function converges to 0. Pointwise convergent, we know that, and this function is continuous, so we have to use MN test here. And here again we got a function. We have to find the supremum of this function in R. And for that, I again consider its derivative and consider where it is going. And when you equate the derivative to 0, you will get x equal to plus or minus 1 by root of 2n. And here x has two values, plus 1 by root of 2n, and the second value minus 1 by root of 2n. By substituting these values to fn of x, you can see which one gives the maximum. And here you will get the maximum value when x equal to 1 by root n. So now you plug in that value to your supremum function, then which is exactly the fn of 1 divided by root of 2n, and then we get 1 divided by root of 2n e raised to 1 by 2 is the mn. So mn is 1 divided by root of 2n times e raised to 1 half. And where does this mn converges to? So here it is very clear that it converges to 0. So we qualifies the Mn test. So Mn converges to 0, hence our function converges uniformly. So the option B is correct. I hope I am not going very fast and you can understand it. If you feel that I'm a bit fast, please let me know. I can slow down.
Ma'am. Hello.
Hello.
Ma'am, I have one doubt for question number A. So previously you said stated one theorem that if Fn is continuous and converges to continuous function f, then it is uniformly convergent.
Then Fn is continuous and Fn converges uniformly, then f of x is continuous. So if Fn is continuous and f is continuous, doesn't imply that the convergence is uniformly. The condition is that Fn is continuous and Fn converges to f. If these two conditions holds, then f is continuous. And sometimes we can use the negation, which says that if Fn are continuous and f is discontinuous, then their convergence is not uniform. That is the only thing we can do with the continuity of f of x. If the f of x is not continuous, and we know that fn's are continuous, then we can clearly say that their convergence is not uniform. But the other way around, we cannot say. That is, if fn's are continuous and f of x is continuous, we cannot say anything about their convergence. So the theorem is fn's are continuous and it converges uniformly to f of x. Then, in addition, we know that we can say that fx is continuous. That's the theorem. Is that clear?
Rosna,
Yes.
let me add something in that about that question.
Yes, sir.
Actually, there is a theorem called Binny's theorem, which
Okay,
says
that
that if the sequence functions are continuous and the limit function is also continuous, then the convergence will be uniform, provided the sequence should be a monotonically increasing one and the domain should be a compact set. So such a convergence is available, but some restrictions are there. But in this case, okay, that won't work because I think we don't have that conditions. So such a result is also available. Okay.
Okay. Yeah, I saw that, but yeah, I didn't mention it because it was in there, so I didn't give much attention to that result. So
yeah, it's okay.
Thank you so much for pointing it out. Okay, that is nice to know that there exists something, because for net question they might ask such things that, okay, assume that Fn is continuous and monotonically increasing, can it be convergent? Yeah, so these results are also very nice here. Thank you, sir. Okay, then let me go to the next question. So this is again asking for uniform convergence in open interval 0, 1. The first set of function is x raised to n. The second one is n divided by nx plus 1. Next is x divided by nx plus 1. The third one is 1 divided by nx plus 1. So these functions looks very similar to each other, but you can see which ones are uniformly convergent or not. These questions you can always expect in examinations. They just change a little bit. You put an n here or nx here, then maybe put nx square or something. So these kind of looking functions are very common. So if you would like to do more questions, just make some changes. So what if I put an x here? Or what if I put an x square here? What if, does it change if I put an n square x here? So this is a technique we can maybe use to manipulate some questions and see whether it is uniformly convergent or not. So this is a bit different, but the rest is looking very similar. But let's see which of them are uniformly convergent or not. So I will again give you around 45 seconds to solve it. Let's see the answers. Please comment it on the chat. Even if it is wrong, that is fine. You are just trying for 45 seconds, so mistakes might happen. But don't worry, you just post it, then you will get an idea of how we are thinking, or are you in the right direction or not. So I'm getting solutions as A, C, A. Okay, let's see what all other answers could be. D, A. Okay, there are a lot of answers. Thank you for your solutions. Let's look at the final solution. Now, first take fn of x is x raised to n. As we have seen before, we have to find to which function it is converging to. So here we have the x from 0 to 1. So x raised to n is between 0 and 1, hence it is converging to 0. So f of x 0. So far, good. We are getting to a nice continuous function. But here we cannot predict anything about our convergence. But for that, I am using Mn test again. And I'm putting the values of fn of x and f of x. And my range is from, the domain is 0, 1. And if you have x belongs to between 0 and 1, then the x raised to n is also between 0 and 1. Then the supremum of x raised to n can be said as less than 1. Then mn's are 1. So the sequence of mn is just 1, the sequence of constant function. It is not converging to 0. So this function is not uniformly convergent in this interval. Okay, now let's check the second case. The cases which are very similar to each other. The first case is n divided by nx plus 1. Again, we have to find where this is going to. So if you don't know the technique, one of the easiest technique is to take out the n outside. So then you will get something like 1 divided by x plus 1 by x. Here, x is kind of a constant, only n is moving, and you know that 1 by n converges to 0. So you can easily say that this is going to a function 1 by x. So your limit function is 1 by x. And now you have to check, so this also doesn't say anything about your convergence. So you have to check for mn. So now for mn, you have to find the supremum of fn of x minus f of x. So here it is. So I'm just multiplying, so making the denominator same. And by cancelling out, you will get 1 divided by x into nx plus 1. But when you consider the mn, the supremum of this function, this is infinity. So you cannot get an mn which is converging to 0, which implies that your function is again not uniformly convergent. So the function of the form nx divided by nx plus 1 is not uniformly convergent. Now let's consider the next case. You just replace n by x and see what happens. So now take the next function, which is x divided by nx plus 1. So what should be the limit function here? It is 0 because you have the n only in the denominator. So it is easy to say that it converges to 0. And here also we again have to look at the mn. And you are trying to find the supremum of x divided by nx plus 1, which you can see that this is 1 divided by n plus 1, the supremum of these functions. And where does this 1 divided by n plus 1 converges to? Clearly, it converges to 0. So you have this mn, which is converging to 0, which implies that your function is uniformly convergent. Oh, sorry, I type it wrong. So it is uniformly convergent. It's not uniformly continuous. It's a different topic, sorry. So this is the correct answer. And now let's check what happens with 1 divided by nx plus 1. So option C is correct. Let's check what is option D. You have fn of x, which is 1 divided by nx plus 1. this is clearly converging to 0, you again use the Mn test. You are taking the supremum of this function, and when you try to take the supremum, you will get it as 1. So the Mn does not go into 0, so Fn is again not uniformly convergent. So the option C is the correct one. I hope that you understood the solution. Let's move to the next question, which is already appeared for GATE 2017. So some of the previous questions are already appeared for GATE or NET, but I don't remember in which one. That's why I didn't mark it. But this question is from some previous question paper. It's but this one I remember which question paper it is. So it is GATE 2017. So let's look at the question. So this question looks very complicated, but it is not that complicated. So we have a function, and the function is given by 2x squared divided by x squared plus 1 minus 2nx the whole square. And this function is from, in the domain is 0, 1. And we have to check the following. The first one is this function converges uniformly in 0, 1. The second option is it does not converges uniformly on 0, 1, but it has a subsequence that converges uniformly on 0, 1. The third one is that it does not converge pointwise on 0, 1. The fourth is that it converges pointwise on 0, 1, but does not have a subsequence that converges uniformly on 0, 1. So this questions, it is you can predict something from here, not prediction, but you can have some connection. If your function does not converge pointwise, then clearly it will not converges uniformly. And you can again cross out another options. So in some options, if you get something as wrong, then the other options might be automatically crossed out. So first you check whether the convergence is pointwise. If so, check whether it is converges uniformly. If it is true, then A is true. If it is not, it does not converges uniformly. Then you have to find whether there exists a subsequence that converges uniformly. If it is not, then the option D will be true. So this looks a bit complicated, but it's not that complicated. So I will give you maybe around 1 minute if you want to do this, because you have to do a little bit of calculation. And when you get answers, please let me know in the comments. So it's almost 1 minute, but I haven't received any comments yet. Okay. Could you say the difference between pointwise and so for the pointwise convergence, your value of n, or you're looking at with each point x whether it is converging to your final the function f. But for the uniform convergence, this it should be pointwise convergent, and the convergence should be kind of a uniform. So you are taking, so how you say that a sequence is converging? You say that for up to after some n, it is going to your limit function. So when you say pointwise, it is enough to show that for each value of x there exists some n which is going to the limit. But for the uniform converges, this n should be valid for all values of x. That is the main difference from pointwise and uniform convergence. So if you can prove something, for example, in this function, if you can say that for each function x, this is going to some function f, then it will be pointwise convergent. But if you want to say that this is uniform convergence, then this going to the function should be in a uniform basis, that you get a common n. So in order to, since it is difficult to find a common n for your all x, you are just using the MN test, that you are taking the supremum of fn of x and f of x and see whether that supremum is going to 0 or not. So this is an easy method to show that your function is converges uniformly. So did you get any solution to this question? So what do you think, whether this function converges pointwise or not? That will be the easiest question to answer. Could you just answer me in the chat? What do you get it?
Yes, ma'am.
Yep. Okay, there is option B. Okay. So you got that the function is not uniformly convergent but has a subsequence that is converges to. Okay, there are option A. Okay, you got it as uniformly convergent. Okay, I'm not leaving much time. So let's see the solution. So first of all, you want to see whether function converges pointwise, that is for each value of x where it is going to. And for that, you take the limit n tends to infinity of this function. And for x equal to 0, when you put x equal to 0, then clearly this function is 0. And for x is not equal to 0, and you treat the x as some kind of constant, then again you can see that this function converges 0. So for all values in 0 and 1, this function is going to a 0 function. So is that clear, I guess? So this function is going to an f of x, which is a 0 function. So from this process, it is clear that your function is a pointwise convergent function. Just a moment. Okay. And now this question, so let's come back to the solution. The solution C says that it doesn't converge pointwise, so that is wrong. It converges pointwise to a function. So option C is wrong. So the next question is whether it converges uniformly or not. To find whether it is converging uniformly, the test is the MN test that I defined already mentioned before. And for that, we have to find the difference between fn of x and f of x and take the supremum. So since our f of x is 0, you just want to find the supremum of our given function. And how to find the supremum? We use the same method. You consider this function as some y or some g of x or something, and you take the derivative, and you get the derivative to 0, and you get some maximum or minimum points, and you check what you're obtaining there. And here, when you substitute these values, you will get x equal to 1 by 2n. And when you substitute it, and you will get the maxima of the function. And by simplification, so I just avoided all the simplification. You can try to see what you're getting when substituting these values. But when you substitute this, there will be a lot of cancellations, and you will finally get Mn converging to 2. But here, we need Mn converging to 0, but we are getting Mn converging to 2, which means that this function is not uniformly convergent. So the option A is wrong. So we are left with two options. It does not converge uniformly on 0, 1, but has a subsequence that converges uniformly on 0, 1. Or it converges pointwise on 0, 1, but does not have a subsequence that converges uniformly on 0, 1. This is kind of two opposite answers. So we know that it does not converge uniformly. So this part, up to this part is correct. It converges pointwise on 0, 1. So up to this part is correct. So the first portion of both of them are correct. But the second portion is the confusing part. It has a subsequence that converges uniformly. Others says that it does not have any subsequence that converges uniformly. So this is kind of an opposite ends. Only one of them will be true. So let's see whether it has a subsequence, converges uniformly on 0, 1. So how we can see whether it has a subsequence? So we didn't know anything about the subsequence of convergence. So how can we say something about a subsequence? So what we can do, we know that if we have a sequence that is converging to something, then if we know that if it is converging to some L, then all the subsequence also converges to L. This is we know. Then in our case, let's take our function fn of x. Suppose it has a subsequence that is converging to something. That converging thing will be 0. So the any subsequence of your fn will be pointwise convergent to 0 only, because our whole function is converging pointwise to 0. So the subsequence also converges pointwise to 0. So that part we know, but we have to show that whether this convergence is uniform or not. So for that, we again take Mn of this. This is not so here. Don't confuse it with the derivative. I'm just taking m dash to separate it from your previous mn. So it's not the derivative of m dash. It's just the another mn. So let's consider that fm is the subsequence, and I want to find the mn of these fms. And I had to say the supremum of that value should converge to 0. Then only we can say that this sequence is uniformly convergent or not. But how do we know that whether such a thing exists? But here we again use the same one. So these mn's are the subsequence of our original mn's. So you have some mn's which is obtained from your original fn's, and these subsequence fm's also their corresponding mn's will be a subsequence of this original mn's, and we know that this mn converges to 0. So whatever subsequence you have in mn, that will also converges to 2. So converges to 2, then the subsequence also converges to 2. So this mn dash of n, which is the subsequence, which is also converges to 2. So it cannot have any subsequence which is uniformly convergent. So the option A, B is wrong. It does not have any subsequence that is uniformly convergent. Is this question clear? I know that it is a bit complicated to think. Is this question clear to you?
Yes, ma'am.
Okay, thank you. So just but you have to remember one more thing. If you cannot prove that something is uniformly convergent, or if it is not uniformly convergent, it doesn't mean that there exists a subsequent which is uniformly convergent or not. There can be cases that your function fn does not converges uniformly to some function, but there exists subsequent which converges uniformly. So from this question, you should not think that, okay, if something is not uniformly convergent, the whole function, it cannot have any subsequence which is uniformly convergent. That is wrong. It might have a subsequence. We don't know. But here, we could prove it because we know all mn's are converging to 2. So its subsequence also converging to 2. That's why we proved it. Okay. So maybe let me see whether I have an example of that. Okay. Consider this function fn. So this is just an example to show this result. And here for the fn, I define the functions f2n minus 1 as 1. So which is a constant function 1. And for f of 2n, I define it as x raised to 2n. And together with them, I'm getting the sequence fn. And I define everything on 0, 1. So what does this fn converges to? So this function converges to both 1 and 0. So it is not a pointwise So this is not a function. So this is a pointwise convergent function. Yeah, for each point it is converging, but for it is not a uniformly convergent function because you have some values as 1 and some values as 0. But what happens to a subsequence? Does it have any subsequence which is uniformly convergent? Actually, yes, because this sequence 2n minus 1, this is always 1. This is a sequence of just 1. So you draw 1 lines, and this sequence converges to 1 uniformly because it's kind of a constant sequence. You say 0, 0, 0 converges to 0. Yes, so 1, 1, 1 converges to 1. So this is a kind of a constant function. So their convergence is always uniform. So if you consider Fn, they are not uniformly convergent, but it has subsequences which are uniformly convergent. So you have to remember that there might exist some subsequence which does this uniform convergence thing, but you have to be careful. I hope I didn't confuse you much about this regard. Okay, let's go to the next question, which is again taken from a net examination. Let Fn of x is equal to 1 divided by 1 plus n square x square. Then which of the following are true? The first option is Fn converges pointwise to 0, 1 to a continuous function. So we have to check whether it is converges pointwise. If so, is it converging to a continuous function or not? The second one, Fn converges uniformly to 0, 1. Third, Fn converges uniformly on 1 by 2, 1. So here the domain has changed. So if it is convergent in this domain or not. And third, limit n times to infinity, integral 0 to 1 Fn of x dx is equal to integral 0 to 1 f of x dx. So these are the 4 options. Maybe I will again give you around 1 minute to think about it, and please comment your answers in the chat box. Mm-hmm. So what you have to do here, you first check what is f of x. And if you could find f of x, then it is pointwise convergent. And see what is the f of x, whether it is a continuous function or not. If it is a continuous function, then option A is true. Then check whether the convergence is uniform or not. If it is uniform, then option B is true. But if it is converges or 0, 1, then definitely option C will be also true. But if you already prove that Fn converges uniformly on closed 0, 1, then Fn also converges on 1, the half to 1. So that is a kind of a bonus. But if you cannot prove it for 0, 1, then you have to calculate again for the other one. And the last one, if it is uniformly convergent, the last one is also a bonus for you. You can take it. But if it is not uniformly convergent, then you have to check the answer. Okay, I'm getting few solutions. Okay, let me discuss the solutions. Okay, what we have Fn of x, which is 1 divided by 1 plus n square x square. Our first task is to find what does it converges to, and our interval is 0, 1. And when x equal to 0, then you put x equal to 0, you will get f of 0 is 1. So all the fn of 0 is 1, so it is converging to a f of 0, which is 1. And for x is not equal to 0, so you can treat x as some a, then this function is going to 0. So for all values not equal to 0, they are converging to a value 0. So our f of x is 1 when x equal to 0 and 0 when x is not equal to 0. Is that clear? So from here it is clear that the f of x is not a continuous function. So fn converges pointwise on 0, 1. For all values of x, you have the f of x. They exist, so it converges pointwise. But the function is not continuous. So the option A is wrong. So what can you say about option B? So I have already told several times what you can know about option B. Can you say it in the comment box? What should be the option B, whether it is true or not?
Yeah, B and C also wrong.
Yeah, okay, let's see whether both of them are wrong or not. So as I mentioned several times, Fn is the collection of continuous function, and if it is converges uniformly, then the function should be continuous. But we have the collection of continuous functions, and then our f should be continuous. But in my case, f is not continuous, so this the convergence is not uniform. So B is wrong, the convergence is not uniform. But what happens if I change the domain? If I change the domain, if x belongs to half and 1, then my f of x equal to 0. Why? Did you remember the function? So f of x is 1 only when x equal to 0. So if I remove the x from my domain, then f of x is 0. So in this case, the f of x 0, so we cannot use this function, use this theorem, because my f is continuous. So we have to check it via MN test. Now consider this function, and we have to find the supremum of our function, and how we can find the supremum. So this is one way. So previously I gave you a way in which you take the derivative of the function and equate it to 0. And this is another way you can just plug in what the x is. So you know that the x is between half and 1. Now take the x square. You have 1 by 4 is less than equal to x square and 1. So you multiply with n square. Okay, then you have 1 by 4 n square is less than equal to x square n square is less than equal to n square. You add this 1. So 1 plus this value is less than equal to 1 plus n square x square is less than equal to this one. And now you have to take the reciprocal. So you take the reciprocal, so the signs reverse. So you will get 1 divided by 1 plus n square is less than equal to 1 divided by 1 plus x square n square is less than equal to 1 divided by 1 plus 1 by 4 n square. So the supremum of this value is so this value is less than equal to 1 divided by 1 plus n square. What does this goes to? This goes to 0. Because when n goes to infinity, this one function goes to 0. So you will get mn goes to 0. So for x belongs to 1 by 2 and 1, this function is uniformly convergent. So this answer is correct. Now, in this range, we know that it's uniformly convergent, but again, for the limit, it is from 0 to 1. If it is from 1/2 to 1, then we can directly say that, yeah, this is correct because it's uniformly convergent. But for 0 to 1, it is not uniformly convergent. So you cannot guarantee that this result is equal or not. But we have to check it directly, what is happening between the limit and integration. Now let's take our function from 0 to 1. Fn of x dx is integral 0 to 1, 1 divided by 1 plus n square x square. When you try to solve it, you have some expressions like 1 divided by n square plus x square kind of formula. When you plug in that formula, you will get 1 by n tan inverse of n. So this is the integration, and you have to apply 0 to 1, then only you will get this value. And where does this 1 by n tan inverse of n goes to? So this is when n comes to infinity, what happens to tan inverse n? So what is tan inverse of infinity? So when n goes to infinity, the tan inverse of infinity is actually pi by 2. Then you will get this whole thing when limit n tends to infinity, the whole thing is going to 0. So you get the first part, limit n tends to infinity, integral 0 to 1, fn of x dx. So this part is 0. Now we have to check what is the second part is. The second part, the limit n tends to infinity fn of x, we have already found out this is our f of x, which is 1 when x equal to 0 and 0 when x is not equal to 0. But since we are taking the integration, we can clearly say that the integral f of x dx is equal to 0. So they are actually equal. So this part is equal to 0 and the second part is equal to 0. So option D is correct. Is that clear? I hope so. So let's move on to the final question. If gn of x equal to x divided by 1 plus nx square for x belongs to R, then yeah, thank you. Then which of the following is correct? Option A, whether this collection of Gn is not uniformly convergent. Option B, so here you have to check. If you didn't read the question clearly, then you will get confused. In the first case, you are just considering the function Gn of x, which you have to say whether it is uniformly convergent or not. The second case, you are considering the derivatives. So you have a Gn, you now consider the derivatives of each of the Gn, whether this sequence converges uniformly in every interval not containing 1. Now again, the derivative sequence converges pointwise to a continuous function, whether the derivative sequence converges uniformly in every interval not containing 0. So in one case, you are just dealing with the functions gn of x. In the other case, you are looking at the derivatives of those functions, what that converges to. So this is the 7th question, and I will give you around 1 minute because you have to calculate the derivatives. And if you get the solution, please let me know in the comment box. I haven't received an answer so far. Maybe it might take a little bit time for you to calculate. So I will give you a little bit more time. Try to solve this and then we can solve it together. Were you able to calculate the derivative of the function and see? Okay, I'm getting some solutions. Let me see and wait for a few more seconds then, so that whether I get some other solutions or not. Okay, there are solutions like E, A, and C, and A and C. Okay, let's see what happens. Okay, let me tell you the solution. The first one is that we have the function gn of x, which is x divided by 1 plus nx square. Then I am trying to calculate its derivative. So I am taking the derivative, and when you do the calculation, you will get 1 minus nx square divided by 1 plus nx square the whole square. So we have a collection of these functions, and we have to show whether this function is uniformly convergent or pointwise convergent, whether it is convergent to a continuous function or not. So if x equal to 0, when you put x equal to 0, you will get the function as 1. For x is not equal to 0, you can take it something like 1 minus na square divided by 1 plus na square the whole square. Now we have to see for n terms to infinity what this function going to. If you don't want to do a lot of calculation, you can just maybe think of, okay, this is a function kind of n. You have only n here, but in the denominator you have kind of n square. So the more fastest one will be the denominator, so it will go to 0. So clearly what you get, the derivative functions will converge to some function. This is actually 1 for x equal to 0 and 0 for x is not equal to 0. So this function gn dash of x converges pointwise to a function because this convergence exists for x, but the limit function is not continuous. So we are getting a discontinuous function. Let's see whether we can rule out some options. Yes, the option C is wrong because it converges pointwise, that is true, but it is not converging to a continuous function. So whenever you are checking for g dash of x, I felt like you are missing out some points. So you have to check it. So when you consider the range, it is from x to r, so you have to check it for all values of x to r. So you when you see these functions, you first think about what happens to this function, and then you can see that, yeah, if I put x, if the x is not there, then function is 1. So if you miss out these some points in which the function behave a little different, then your answer can go wrong. So usually the x equal to 0 or x equal to 1 kind of things makes issue. So if you get a function and if you're not sure about where it converges to, first put x equal to 0 and see where it is going. Okay, it is going to 1. Now you can just delete it and see where it is going. So this is actually going to a discontinuous function. So you always check it for all values of x and see where it is going, because in some values it might behave differently. So option C is wrong. Okay, now what about the different intervals? So in order to take x belongs to R or x belongs to a different interval, so you are restricting the domain, whether it converges uniformly or not. That question we have to answer, and also we have to check whether your original function is uniformly convergent or not. Okay, let's now maybe let's consider this question. We are looking for some interval not containing 1. Okay, for example, I'm considering an interval minus half to half. So this interval does not contain 1. But what happens in this interval? Again, the same thing, because when x equal to 0 exists here. So when x equal to 0, the value is 1. For x is not equal to 0, you have value 0. So again, this function converges to a discontinuous function. So the converges uniformly is wrong. So maybe here you can think about something. does it converges uniformly in every interval not containing 0? So here we have a more chance, because in these two cases, we saw that the 0 is actually making your function discontinuous. So if there is no 0, your function converges to a 0 function, so it is nice. So there is a chance that it converges uniformly, but you cannot say completely whether it is converges uniformly or not. That we can check, and we also left with Gn of x. So I'm just leaving it here, and I'm just going back to Gn of x, what you can say here. So now we have Gn of x, which is x divided by 1 plus nx square. And when you substitute the value, when x equal to 0, it is 0. When x is not equal to 0, again, yes, it is going to 0. So this is going to a 0 function. Nice. So there is a chance that it could be uniformly convergent, but we don't know. We have to do the 𝕚𝕚𝕚 test. So now I take the supremum of Gn of x, and here the g of x is 0. Then you just want to find the supremum of this function. And here our R is, so here our domain is the whole R. So we have to check it for all values of x. So I'm just restricting to see what I'm getting. So first I assume that the modulus of x is less than or equal to 1. Then in this range, I'm just trying to see what is the maximum value of x divided by 1 plus nx squared. And when you, here you again consider the Gn dash of x, and when you evaluate, you will get when x equal to 1 by root 10, it attains the supremum value in this range from -1 to 1. So I put the value x equal to 1 by root 10, and I will get 1 divided by 2 times root 10, which is going to 0, then it is fine. So if my x varies from -1 to 1, then this function converges uniformly. But we have to know it for all values of x. So this is just for x from -1 to 1. So what happens for the remaining? So now I assume, okay, x is greater than 1, and what happens to my supremum? So here I consider, so the supremum is nothing but the Gn of x modulus of value, and I split the modulus, and this modulus of divided by 1 plus nx square. So you have something like 1 plus nx square. So if you remove 1, the denominator getting smaller, then you will have this is less than or equal to x divided by nx squared. So here you can cancel this x because the x is greater than 1. And then you replace the x with 1, and you will get something like 1 divided by nx. And here you can say that this function is again less than or equal to 1 by n. This converges to 0. So you get that for all values of x, your Mn is converging to 0. Hence, you have a uniformly convergent function. So your Gn of x is uniformly convergent, but the option says that it is not uniformly convergent. So these 3 options are wrong. So the only possibility is that this is correct, but we have to check whether it is correct or not. Now we come back to the Gn of x, and we are considering an interval not containing 0. And when you have something not containing 0, then the as I mentioned before, this discontinuity part is removed. That is good. And now we calculate what is the Mn for that case. So for Mn, we have Gn dash of x minus our f of x, which is just 0. Then we have to find the supremum of this function, and when you calculate it, you will get it as 1 divided by n square x raised to 4, which is converging to 0. Hence, Gn dash of x converges uniformly to 0 for all values not equal to x. So if you consider any interval which does not containing 0, then it converges uniformly. So this completes my questions, and thank you for your attention. Do you have any further questions or anything else to know?
My name's
Yes.
Alina. I'm third year student of Marthoma College, Tungatra, Kerala. Thank you, ma'am, for such a wonderful class. This was an entirely new topic which you have not covered. You explained it so well. Thank you, ma'am.
Thank you so much for hearing that.
Especially
I
the
feel
questions
happy.
you have discussed. They are very well detailed explanations. Thank you, ma'am. Thank you, Vinod sir.
Thank you, Alina.
Yeah, thank you very much, sir, for giving this opportunity. And this is very nice to interact with people and to brush off some of my memories because it's quite long that I have done, go through the convergence and things. So it was also a nice opportunity to go through the things again.
Ma'am, my name is Subhra Kundu and I am from West Bengal. So, ma'am, graphical representation of uniform convergence is very unique. It is too much very easy for understanding. Overall topic is very unique and so it is understand very easy. Thank you, ma'am.
Thank you.
Thank you.
Yes, thank you so much for your feedback. It means a lot. Thank you very much.
Ma'am, my name is ℕ𝕠𝕟𝕚𝕚𝕚. I'm in first year M.Sc. Just talking about this concept perspective, it was really intuitive, and the way you explained point-wise convergence and uniform convergence graphically, it was just like reading Kumara's book. That's really, I really like the way you
I also attended his classes.
and it was very evident that you took a lot of effort in creating those slides and all. Thank you, ma'am, for the wonderful session. And sir, always thank you, sir, for arranging this.
Yeah, thank you, Nalin.
Thank you very much for attending this section and making it a
success.
success.
Attending many lectures from experts is always having many positive things. You will get something to copy from them.
Yes,
so
yes.
That is
Combinations are always define things into the conceptual ways, and I attended MTTS 1 and MTTS 2, if I remember. So they explain everything from the basis. So that's why it was also easy for me to recall things, because it was almost 3 or 4 years I touched this part. So in the beginning I was like, oh, I forgot many things, but when I reading I can remember or recall their classes. So it was easy. So I also recommend you all to attend those classes like this MTTS courses. When you're studying, you might not be using directly to your proof, but later if you want to recall something, it is very easy, because this gives you an impression of what the definition is. Then just by hearting for all epsilon, for all x, you will get confused with all these sentences. So it is nice to see something in front of you, then you can remember it.
Yes. Sakshi? Yeah.
Hi, ma'am.
Yes.
Good evening.
Yeah, Ananthi. Yes.
I feel it's a very complicated topic as a uniform convergence, but you came teach us very easy. I feel now it is very easy for me. Thank you, ma'am. Thank you so much for your effort. And thank you so much, ma'am. I really enjoyed the topic and I listened it very sincerely. Thank you, ma'am. Thank you, sir, for organizing a wonderful session.
Yeah,
thank you, Ananthi. You were answering. I was seeing your comments. So thank you for your courage to answer it in the comment box. So many people will be a bit of afraid to answer by thinking that whether it is right or not wrong. So I appreciate your courage to answer in the chat box. Thank you for the cooperation.
Thank you, ma'am.
Hello, ma'am.
Actually, I was.
Hi, sir.
Yes. Yes.
My name is Arya K, and I'm currently BSc Maths final year student from Kerala. First of all, thank you, ma'am, for such a wonderful class, and it's really helpful to solve the questions from uniform convergence. And thank you so much, ma'am.
Thank you very much for being here. Thank you so much.
Hello, ma'am.
Yes.
I'm Gayatri. I have studied in Miranda House College, Delhi. It was really a nice class and was easy to understand the concept because of your clear explanations. And I'm so thankful to you for taking such a wonderful class. It was really useful. Thank you, ma'am.
Thank you very much. It really appreciates me to take more classes.
Yeah, you have to. You promised me to engage one more session on uniform continuity this time.
Yeah. Next time I will take the uniform continuity.
Hello, ma'am. Hello,
Yes.
sir.
Yes.
Yes.
I'm Shikha, a second-year MSc student from Birla Institute of Technology, Meshra, Jharkhand. Ma'am, your session was really wonderful. Your explanation was very detailed and it was easy to understand. Overall session was really nice, ma'am. Thank you.
Thank you. Thank you so much
Thank you,
for
sir,
being here.
for organizing such sessions.
Thank you, Shikha.
I'm Nandra Jayavarma from Zamurian's Gurarpan College. And thank you, ma'am, for this informative section and for your valuable time. And thank you, sir, for organizing this. Thank you so much.
Thank you. Thank you very much.
Hello, ma'am.
Yes.
Yes.
Ma'am, I am Tithi Biswas, MSc second year student. Ma'am, today's session was really wonderful. You explained the topics and as well as you explained through examples. So it was really nice to understand. And I really feel thankful to attend this session. And thank you so much for your giving this valuable time to us. Thank you so much, ma'am. And thank you, sir, for organizing this session.
Presently from Vizag. I am doing library job in BARC Visakhapatnam. Session was very nice and explanative. Kindly can you suggest some reference book and textbook and PhD experience, your PhD experience also. Thank you.
Okay, I will start with maybe my PhD experience. So I was studying in CUSAT, Kerala, for my masters. So after that, I also done the MPhil in CUSAT. If you are trying to do PhD abroad, I would suggest that you should do something good for the master thesis. So most of the time we neglect the master thesis because you are already in the course. You have to finish the course in together with that you need a master thesis. So sometimes in colleges, especially in Kerala, I know that the people won't give much effort to your master thesis. That I can understood. I also didn't do too much into my master thesis. I mean, we don't have, actually I didn't have a master thesis. So that's why I go for MPhil, and I have an MPhil thesis, which I get 6 months for just for doing the thesis. That was helpful for me to go abroad. So if you are trying to go abroad, you just do a bit more work to your master thesis, then it will show yourself to others that okay, you are capable of working on some topic, like that. So when you're studying a bachelor's or a master course, try to do a bit more into the master thesis, and always try to find somebody from other colleges to like a collaboration. So even if you didn't get somebody from IIT or NIT, that is fine. If you can show that you are doing something else from your university, so you are taking some effort to get somebody else as a co-author, that is also nice. So try to do that, and maybe I can give more information about PhD in a different section, or would you like, sir, to give more information in this section? Or do you prefer, sir?
Yeah, we can do it in another session, an exclusive session we can plan.
Okay.
Hello, ma'am.
Hello.
Hello. I want to ask a question. Which book is best for JAM entrance examination?
I usually go with the usual textbooks we have in the course book for the relay analysis, and I usually won't prefer problem solved textbooks in the first place. But the only thing I really recommend to you is to do the question papers. So even if you didn't took a book and study everything, but just go with the question papers, because many of the questions are a little bit tricky or little bit be changing. So as I showed in one example, you have x divided by 1 plus nx, then you have n divided by 1 plus nx, maybe nx divided by 1 plus nx. So these kind of questions might come, and the method is same. So whatever textbook you look at, you can see that you can use this MN test for solving it. But only with the practice of solving the question paper, you will be able to cover it. So I'm not an expert of which textbook to use, but for me, what helped me is mostly the question paper solving. Because when I was studying for NET, I also looked a lot on the textbooks you have for your MSc. I try to solve, try to learn every theorem in the textbook, and then I thought only after learning all these theorems and things, I will do the question paper. So for the first year, I tried to learn this. Then I didn't do the question paper. Then for the exam, I got panicked. I didn't do anything well. Then finally, I realized, okay, doing the question paper give you some courage to answer questions, and that will help you. So that is my opinion. Maybe I think sir can give more information of which textbook, because he's more dealing with this.
Yes, actually, you can. Okay, the best way is to practice more and more problems. You can look at the previous question papers. All are available in the JAM website itself. And there are 2 real analysis problem books by AMS, American Mathematical Society, Problems of Real Analysis. That books consists of very good problems. You can have a look at that also. I think that books are being shared in our WhatsApp groups. You can. Otherwise, also you can message me. I will share it. Okay.
I want to only one question again.
Yes.
Ma'am and sir, now I'm in BSc 3rd year, and I want to get examination next year. Then this is right or wrong? Full prepared.
So you're in the 3rd year of BSc, right?
Yes.
And you would like to clear the NET examination next year?
Yes, ma'am.
Yeah, you can try for it. There is no issue. It's better to try as early as possible than making it late. Don't think that only the people who finished MSc could pass the NET exam. That is a misconception. You can just go through the paper and see which are questions you can answer now. Maybe some concept you haven't learned so far, and then try out those questions and try to see the definitions. And I think you can do it. There won't be much issue unless you try the question papers. Just go with the question paper. You will be able to do it.
Okay, ma'am. Thank you.
So do you also have to add something? Yeah.
Yeah. Actually, few of our members, many of our group members were cleared NET during their first semester MSc itself. See, we have a participant, we have one member, Diya Saha from IIT Bhubaneswar, another Jassim from IIT Madras. All they have cleared CSIR NET examination in the very first attempt itself. Actually, it is during MSc is the best time to clear such exams. Okay.
Yes. Don't think that you have to learn everything before that.
See,
but not well according to JAM examination.
Sorry?
My preparation is not well according to JAM examination. My preparation is starting according to BSc examination. So I think I want to appear in this examination in next year.
See, Sakshi, the point is that what Rosna taught, as early as possible. That should be your motto. Don't think that we can wait for one more year and that. I think it is always better to try to clear it this time itself. No need to worry about that, because there are at least 100 days left out for JAM examination. Within these days, you can do wonders. If you have a strong desire and passion and you are ready to do hard work, then certainly you can clear it this time itself. See, after all, it is a matter of only attempting 60 questions. So it is not a big task. It's not a Herculean task. You can do it. So be confident and be optimistic and show that you will clear this exam this time itself. Okay, that should be your motto, at least for the time. Okay.
And even if you feel not that confident, just go for the exam. At least you will understood which all topics you really understood, like in the pressure. So you are writing an exam under the pressure. So maybe you know the question and you know the answer, but with the pressure and with the time running out, you feel more stressed. So you have to manage that stress somehow. So even if you didn't learn much and you are not feeling like I will clear it, but just go for the exam. And then you can see, okay, how much. So that is also how I learned on which part of the paper, so like real analysis, complex analysis, and so on, which parts I take more time. That I understood by writing several exams. And then I was like, okay, this part is the thing which I get confused, or some results you will mix up. You mix up some theorem, the first part of some theorem with the second part of another theorem, and these kind of things might happen under stress. So you will understand, okay, which one. And when you make a mistake, that is very important. When you make a mistake and you realize after the exam you made a mistake, the next time you will remember it. Oh, I made this mistake. I should not do this one. So I feel even if you are not confident, just go for the exam. It will be only for the good thing. So don't worry. And don't too much pressure. I say that, oh, all of my friends are clearing this time, I'm not clearing it. And if I went to the exam, I didn't clear it, I feel bad. No, don't worry about that. It also have a certain luck, I would say. It doesn't only depend on how much you studied. It's sometimes it also luck. I can tell you that the exam I really studied, I didn't pass, but for the exam I almost studied and I was okay, I passed. So it's not depending on how much you studied and you will get. So it's kind of a luck. It's because of how you manage time or some of the things happening around. So don't think that only if I completely study this thing I will go for an exam. Don't think about that. Just go for it and try to be relaxed in the exam.
Thank you, ma'am. Thank you for your session. And thank you so much.
Welcome. And if you, just a small note, if anybody of you are trying to come to abroad, especially to Austria or Germany for doing masters of PhD, there will be options. But if you are planning to do so, please try to plan yourself a bit further ahead, because if you're coming to these countries, if you're planning to come, so try to learn German as early as possible. Because after you're coming here or joining to a course, it is very difficult to manage both German and your course together. So if you would like to do this in your free time, just start it. Then you will have some basic idea of German when you come here, and then you can go for it. Yeah.
Yeah, I think there may be some YouTube channels or websites which helps to learn languages.
Yes, yes. There is many Instagram channels. They will give you shorts. If you're just watching them, then you will learn at least 2 or 3 words, and then you can start your course immediately. So I came here without knowing anything in German, but I survived for 4 years till now. So you can survive, don't worry about that. But I will suggest that you learn a little bit before, then things will be more easy. So just plan ahead which country you are going to. If it is France, learn French, and so like that.
Yeah, that can be taken as a leisure time hobby to learn languages.
Yes, you can download Duolingo and just play it. If you want, you can just, if you don't have any any coaching sessions, you can just download the app Duolingo. Have you played Duolingo? This is an application you can join for free, and they will give you some lessons, not lessons, it's a kind of game. You're just playing it, and you will get some score kind of
link. Please send link of that app. And can you tell about Dark Fellowship also?
I have just placed in the chat. I'm not giving any promotion to them, but I feel it nice. So I also see many of people here are using it, so that's why I recommend it to you. You can learn many languages in it. But if you're seriously considering coming here, it will be better to start learning. Then you will take only less time to catch up than starting from the beginning. Yeah, I will try to give another session on how to survive here, or maybe how to find opportunities, maybe in a different session.
Thanks.
Yeah, I will tell about that for the next session. That I can. I have to do a little bit research on that, so that's why I'm telling that I will give a different session.
We can postpone that into our future session.
Yeah.
Yes, others.
Hi, ma'am.
Hi.
Yes.
I'm Sri Lakshmi from Ernakulam St. Teresa's College. Thank you so much, ma'am, for this wonderful session. It was very helpful for us. Thank you, ma'am. Thank you, sir.
Thank you very much, Sri Lakshmi, for being with us.
Hi, ma'am. I'm Amal. I'm from Iritty Mahatma Gandhi College. The topic was somewhat new to me and somewhat troublesome, but the class had helped me a lot. I think the recording also will be helpful for me to understand more. Thank you, ma'am, for such a wonderful class. Thank you, sir, for organizing such a class.
Thank you, Amal.
Thank you. Hi.
Yeah, Lakshmi.
I am Lakshmi. I am from TMG College, Tirur, Kerala. Today's class was very nice. You explained each topic very clearly. Thank you, ma'am, for spending your valuable time with us, and thank you, Vinod sir, for conducting this class. Thank you.
Thank you, Lakshmi.
Rosna, Lakshmi is actually first year student from my college.
Yes, I heard the institute, so I thought, yeah, it should be from your college. So I wish everyone good luck for the next examination, and please try every day a little bit of the problem solving. Then you will achieve your results.
Malavika is yes, Malavika.
Hello, ma'am. I'm Malavika, third year BSc Math student of St. Teresa's College, Kozhikode. Thank you so much, ma'am, for this wonderful session. It is really helpful for us, and we really enjoyed it. Ma'am, could you suggest any tips for us to crack competitive exams?
Yeah, the main trick is just practice with the time. You just put some time pressure on you and practice the question and try to solve it within 1 minute, or you just calculate how much time you will get for a question and try to solve it like that, because usually if you get a lot of time you will be able to solve it. So it's not that you don't know how to solve it, it's more will be how to solve it in the time pressure. So always try to solve the question paper with the time period, and do this more time, so then you can do it fast. And when you are all also familiar with the questions, then you might remember, okay, this kind of question I already solved, so this might be the trick or something simple. So when you see the questions and you want to say what it is converging to, when looking at the question you can think, okay, which points might go wrong, okay, x equal to 0 might go wrong here, let's put it there and see. So these kind of things we might miss out, but when you practice you can get an intuition of where it is going on. Yeah, I think practice is the key.
Thank you, ma'am. And also I would like to thank Vinod sir for conducting such a wonderful session for us. Thank you, ma'am and sir.
Thank you.
Sir, am I audible?
Yes.
Ma'am, I am Anamika from Kerala, from ℚ𝕚𝕚𝕚 College. Thank you, ma'am, for this session. Actually, this was some tricky part, and this is a new part for me. But it's okay. You explained very well, and I will try these questions repeatedly. Thank you for the session and your valuable time. Thank you, sir.
Yes, thank you so much. If this is a new topic, please do consider solving more questions, then you will get more idea of how it is working. Yeah, I hope that I explained, I didn't confuse you much with the explanations.
No, ma'am, it's clear.
Thank you.
Actually, here it is only in their 6th sem and they are all 5th sem students. That's why.
Okay. I also expected some MSc students, so that's why I thought maybe something is too obvious for people.
Yes. Yeah, any others? If any of you would like to express any comments, you can do it now. Otherwise, I think almost all of them are followed. Okay, thank you, Rosna. Thank you again. Thank you very much.
Thank you, sir, for this opportunity. This was really nice. Thank you, sir. Thank you all and all the best for your exams.
Thank you, ma'am. Thank you, sir.
Okay, let us wind up here. Thank you. Thank you.